So this Daily Brilliant challenge is called Magnetic Protection. It says, space is full of ultra-fast particles called cosmic rays, which would eventually be deadly for human spacefarers without adequate protection. These cosmic rays are generally the nuclei of small atoms like hydrogen and helium, though they can sometimes be larger. All these carry positive charge, which is part of what makes them dangerous. Even worse, they are not blocked by Earth's atmosphere. Luckily for us, however, Earth has another feature that protects us from fast-moving charged particles: a magnetic field. In an electric field, charged particles feel a force. Positively charged particles are pushed in the direction of the field, while negatively charged particles are pushed in the opposite direction. Magnetic fields also affect charged particles, but in more complex ways. These fields arise from electric current from certain materials such as used to make refrigerator magnets. They are also commonly formed around stars and planets, though the mechanism for this isn't always completely understood. A charged particle in a magnetic field experiences a force only under the right conditions. It must already be moving in order to feel a force, but the direction of this movement can't be the same direction as the field. The force experienced by the particle is perpendicular to both the magnetic field and the direction of motion of the particle. For example, suppose a magnetic field points outward from the screen towards your face, commonly represented by circles with dots in them. If a positively charged proton is fired up the screen as shown, it feels a force to the right, perpendicular to both the field and the motion. As it turns, the direction of the force changes as well, so that it ends up moving in a circle. So in other words, if the force of the magnetic field is pointing straight up at you, a proton moving where my cursor is moving, it's going to get bent while it's in this force and turn around, like so. Now suppose the magnetic field is pointed outwards. If the proton is fired parallel to the field lines, it will continue straight and not be affected by the field. So if the magnetic field is in this direction, the same direction as the charge is moving, it won't be affected at all. It'll just move on straight by as if nothing was there. However, if the proton is fired diagonally into the field as shown below, then it will feel a force perpendicular to both its motion and field. This will allow its motion along the field direction to be unaffected, but it will experience a force causing circular motion, as in the first example. This will result in a spiraling motion around the magnetic field. So when it's diagonal, it does continue to move in this direction. However, since it also has a perpendicular component, it circles just like it did when the force was completely perpendicular to the charge. The effect of magnetic fields on moving charges is fundamental to electric motors, electricity generation, and hence most of the technology that makes up the modern world. Today's challenge. The Earth's magnetic field runs in loops from the South Pole around to the North Pole, as shown in the diagram. Which parts of the Earth's surface are best protected from cosmic rays by the Earth's magnetic field? So I'm thinking the part that's least protected is going to be right here, because a proton coming in like this, it's just going to run right along with the magnetic field lines. And if it's parallel to the magnetic field lines, it's not affected by it. However, if we're coming towards the equator here, we're running up against a lot of perpendicular field lines, and that's going to cause it to turn around. So I would think the equatorial regions are most protected and the polar regions are least. Let's see if I'm right. Correct. Explanation. Left-hand rule. So we have the current over here, force of direction, magnetic field, direction of current. According to Fleming's left-hand rule, when current flows and an external magnetic field is applied across that flow, the current experiences a force perpendicular both to the field and the direction of the current flow. In this case, a current towards the Earth is created by the cosmic rays, as they contain charged particles that travel from the Sun to the Earth. To be protected from cosmic rays, the charged particles must be directed away from the Earth. In order to deflect particles, a force is exerted on the particle as the Earth's magnetic field is applied across that flow. Since current experiences a force perpendicular both to that field and to the direction of the current flow, we want the magnetic field to be perpendicular to the particle's movement. At the poles, the magnetic field lines, magnetic flux, point in many different directions, whereas at the equatorial regions, most of the field lines are perpendicular to the particle's movement. Therefore, at the equatorial regions, the rays are deflected the most, and the regions are the most protected parts of the Earth.